P and B vary in a flowing fluid as long as changes are not sharp e.g. shock wave, and the fluid internal relaxation times are rapid. So polymer. So the key thing is at each point, you have a point-to-point variation, but at each point, the properties are related by equations. That's the concept of local equilibrium. Okay? Let me very briefly I'll go here very fast because that's a review not only from Thermo 1 but also from material energy balances. I'll go through very briefly through some balance equations because I don't know if I have a chance to do anything in unison today. Chances are small, so maybe just start up and show you how you run it. But for Wednesday's class, please have Unison installed on your laptops. Bring your laptop for Wednesday and have the software installed.
Will there be a link posted for it on the class website?
Say again?
Will you post up a link where we can get it on the class website?
I already posted
Okay, that's
the
fine.
instructions on how you download it and then how you install it.
Great. I haven't seen it.
I went through it today. It's okay, Brian. Yeah. The Victor's instructions. So, quick review on energy balance. You can do it per mass or per mole. I write for mass, and then obviously should be easy to translate it per mole. So the energy balance has the rate of accumulation, and the energy that we have is total mass times internal energy per unit mass plus kinetic energy per unit mass, which is V squared over 2, plus potential energy, so this is kinetic. If you can't read my handwriting, tell me. Is that large enough for the last rows? Ah, okay, good. And of course, internal. And I'm using, and sorry again for the problem in terminology because we were taking control. Sandor puts a period on top to indicate flows. So m dot are mass flows, so all the streams, if you have k streams entering or leaving the system, capital K, K1 equals to capital K. M dot K is the mass flow of that stream and carrying the total energy. And I'm just putting this in the index K plus Q dot, which is the rate of flow of heat from the environment to the system across the system boundaries. So rate of heat flow into the system. This is the shaft work. Which is the important thing is mechanical energy that does not involve the formation of boundaries.
Sorry, formation of what?
The formation of boundaries
Okay.
doesn't involve the formation of boundaries. We'll be adding the deformation of boundary terms in a minute. So energy that flows in the system without deformation.
Can you give us an example of shaft work?
Rotating shaft.
Turbine. We never. Yeah.
And then we have energy by movement of boundaries. And why is there a minus in front here? Yes, ma'am.
Going back to shaft work, they said turbines, and we did turbines in thermal, but we never did anything with that term.
Is this another
Yeah,
way
we
to call
We
it?
did?
Yeah, we did.
This is another name for it.
Oh,
Negative because as the volume decreases, the energy is.
that's the word.
Exactly.
True.
Yes, this is
So-
another name.
Compressing.
Got it. Got it.
All right. All right. So energy into system by movement of boundaries, but that's not all the terms by movement of boundaries. This is energy by movement of boundaries, not at the points of entry or exit of flows. Those have their own contribution, and that is for each stream, in addition to bringing the energy that comes with the fluid, we have what happens to the boundaries there. And that is mass flow times dV of that stream. So that is work done. I'm trying not to unite my letters to make it more readable. And I'm grateful to Dr. Jones. He made the observation that part of the problem with students reading our handwriting is that we tend to unite characters.
Yours is fine.
Oh, in the background there used to be awards, funny awards, and one year Dr. Jones got the best handwriting award. But I really didn't like the following class. Where's the lot of sense of humor? They gave me the following year the worst handwriting award. Why do they not get best and I get worse? two forces acting on fluid moving in or out of the system. So that's your energy balance. Question? Question?
No.
Everybody okay? Remember the stuff? Let's then move on. All right. And what you did in thermal 1, you didn't like to carry both of those terms together. It was convenient to unite those two terms. So if you unite those two terms, we can take the mass flow rates as common factors, so those two become and it was convenient to define a new state variable, the concept of enthalpy. And enthalpy is simply the combination. Oh, sorry, my U looks like a V, sorry. Right. Okay. So, and of course, I wrote here for mass, the mole would have been, okay, and total would have been. So here's the extensive relationship. This is an intensive relationship per mole or per mass. All right. So that's enthalpy per mass per mole and total enthalpy. Also, I'll point out that the effect of changes here and here are typically very small, and they are usually neglected. Not potentially if you have large changes in height, but if you have a molar form, I'll just, sorry for your notes on this, but mass is replaced by moles, hats are replaced by underscores. And but what about units that don't have any hats or for this, you have to multiply by the molecular weight, the kinetic, and the potential terms. Okay. So basically, there's a molecular weight conversion factor between the two. Also, very often, you combine the shaft work and the BDV work into one work term. Also, in a lot of problems, you have used the integration of these differential equations. And if you integrate them, you get a difference form, which could be essentially this quantity at time 2 minus this quantity at time t1 equals, and those become integral, which is the total amount fed in that time interval. Same thing, integral of T dot will be the total energy that flew in, heat that flew in the time interval from T1 to T2. Does anyone really need to see the different forms of this? Are obtained by integration? You're all okay with that, right? I always get it that I spend too much time on review, so I'm trying this year to abbreviate that time.
Do you have it on notes?
In a book, I mean, this is straight in Sandler's book. All right. Now, I have a little bit of time. I want to do an example that will also allow me to introduce unison to you. And it's an application of the energy balance. So here is the example that I want to do. And it's what is referred to as so here's an example. Let's take a gas, let's say for example nitrogen. So nitrogen at 8,000 kilopascals, 500 degrees C, is steadily exhausted to the atmosphere. With pressure 1 atmosphere, of course. Let's assume that we have good insulation across the valve, of course. This happens above. Let's assume that we have good insulation, so we can neglect any heat transfer from the environment to the gas. Potential and kinetic energy change, and assume we are operating at steady state. So we know the temperature and the pressure in, we know the pressure out, and the question is, what is the exit temperature? And I'll call T2 exit temperature. So the picture of what we have is we have a valve, and let's say this is our valve, and we know the temperature and the pressure coming in. We know the pressure 1 atmosphere coming out, and we don't know the temperature. And I'll assume also to say steady state, okay? So how are we going to attack this problem? We're going to do an energy balance. So let's look at our energy balance. What happens to this term?
0.
Why? Steady state means flat line with respect to temperature. No variation with respect to temperature. So all time derivatives become 0. I'm going to combine these two as enthalpy. So these two are enthalpy. What happens to those terms? What am I doing with those terms? I'm neglecting them, right? So what I have left is 0. Let me write it here.